Okay, welcome back everyone. Now we're dealing with the last chapter of the course, and we are talking about structure from motion problem. We have already finished pose estimation and stereo imaging part. Now we reach to the last part, which will about take 3 different sessions to finalize. Basically, the structure from motion, the general concept where structure is unknown, the camera geometry is also unknown. We don't know anything about just the 2D correspondences of different images we have. And after matching those points, corners, blobs with each other, we will try to estimate 3D structure and also the camera geometry together. Uh, now, first I'm going to start with a little bit algebra, a few reminders. Then I'm going to start in this video. I'll try to explain the E matrix technique. The E matrix technique is something basically considers the metric information of the 3D scene and the metric information on the image planes, how they are related, and from this, how can we find the 3D structure. Right now, we will not go to the pixel coordinate system, assuming that we know the calibration matrix K. Now we will just try to put the fundamental formulas, assuming camera calibration is given to us. Now let's start. As I've said before, I'm gonna just do a little bit some fundamental concepts that I would like to explain. At this point, I would like to put a few maybe remarks for you. Now let's assume I have a camera, a projective camera. There is a world coordinate system here. There is a camera coordinate system there. And many things are related with, in terms of the camera and the world coordinate systems. Now, typically we measure in world coordinates, but the perspective projection is defined on the camera coordinate system. But I would like to remind a few things at this point. Let me start with explaining something on here. Okay, now let's assume we have this case. We have x prime, x, a p point, with two different camera coordinate systems. C denotes the origin of the camera coordinates, and O is the origin of the world origin. Okay, let's assume like that. Now, as you remember, the fundamental formula relating these things are equal to like this. Okay, now please note one fact. Now, this is x prime is with respect to camera coordinate system. Let's forget about this middle portion right now. If x prime is equal to t, then obviously t should be coming from the same coordinate system. If there is a t vector that I have to write, for example, this t vector here, and that t vector starts from this origin of c, this x prime goes to point P, and that goes to maybe the next origin. Okay, therefore, with respect to our coordinate system, with respect to our camera coordinate system, this origin point is basically written in this form. Okay, it's equal to t. Now, for sure, Rx is x is denoted in first world coordinate system. Okay, therefore x is starting from this origin going to this p. Therefore, this number, this vector, okay, basically defined on the world coordinate system. After multiplying with r, you are converting this one. Assuming it's in this origin, we are just assume this x cam is here. We put it onto the same origin, and due to this rotation, after this rotation, r times x is a new vector. Now it is also in the same camera coordinate system. Therefore, this is in the camera coordinate system. This is in the camera coordinate system. After multiplication, this is in the camera coordinate system. But please note, maybe this one. This is in the world coordinate system by itself. Now, why am I telling this to you? Because in practice, although mathematical derivations are always starting from the world coordinate systems, what is happening in the camera coordinate system? How do we denote in the camera coordinate system a vector? Okay, maybe this vector is a model or whatever, something about real life. But I am interested with x prime so that I can make a projection. But this vector in between, when you write a t, it denotes something in the camera coordinate system. I always prefer to work from the world coordinate system. Maybe the camera is moving. I would like to find this vector. Now, if you write this vector in this form, okay? If you write this in this form, now please note, this is something maybe easier to define or use from a world coordinate system, position of the camera 1, camera 2, camera 3, always this is fixed, the other one is changing. But if you write it in this way, then you cannot write this equation. I always prefer to work with this one. But this is certainly coming from this coordinate system. Therefore, please note, this is a t vector from this origin. This is a c tilde vector starting from this origin. And please note, this origin and that origin is not completely on. They are rotated. Now, the way we write this is can be shown like this. Okay. Therefore, if I write, okay, my vector in this form, okay, what should I write here? That's the question mark. Obviously not t. It should be about c tilde because I measure this as a information with respect to the world coordinate system, but it should be in camera coordinate system. Therefore, I can show that if you write it in this way, okay, therefore x minus c tilde, okay, which is nothing but a vector with respect to the world coordinate system. This x minus c, both of them are in the world coordinate system. You can subtract them. As soon as you subtract them after multiplication with r, you are saying that you just basically rotate this one with respect to this coordinate system. Therefore, such a structure, if you write it in this way, you will be able to obtain your result, which means you are talking about this t is nothing but minus r c tilde. Okay? Therefore, this is a little trick that we can use later, but here, what we should understand is sometimes we write as a transformation. This is a transformation relation. But this transformation relation is not very useful because I would like to work with the C tilde type of thing with respect to a world coordinate. Then you have to move your camera. In that way, you have to make this little trick so that you obtain nothing but the rotated version, but using the same fundamental transformation that we have learned. Okay, now another thing is, if you write a projection matrix like this one, okay, this projection matrix is basically giving us nothing but the position of x in our camera coordinate system. Just like here, okay, we are just having an x here, and this is obtained after multiplying with this camera calibration matrix. We are making the projection here, okay. Now, this projection and the whole thing can be written as like a 3x4 projection matrix, which can be decomposed like this, but T is consisting of this minus RC. Now, what I'm saying is this projection matrix, if you take this projection matrix and multiply with C, okay, because we understand that any arbitrary point P in our world coordinate system, I insert it to here, I multiply with this, and I just at the end multiply with the projection matrix, and then I basically in the homogeneous coordinates I obtain the small x, which is P times capital X, okay? Therefore, this is our fundamental relation here, okay? Now, the question is, if I write C, nothing but this point, instead of this P point, I'm writing this point. What should be the result? Okay, that result should be equal to 0, okay? Therefore, that projection matrix should give me a point which is nothing but a 0 for me. And then what I'm saying is, based on this information, how can I write a general point, in my image ray starting from C, okay? Therefore, I'm talking about a ray starting from here. I have an image plane like this. Maybe this is not a very good drawing, but if you start from here, if you go to the infinity like this, there are points on this ray, and in the homogeneous coordinates, we know that a C point and another point, if you multiply both points with lambda and 1 minus lambda, that will be another point in between camera center and the arbitrary point A. Okay? Therefore, this x lambda is nothing but a point. Okay? It's a point, it's a homogeneous point where it is starting with the camera center C and going to the infinity like this, okay? Therefore, lambda parameter is just showing us where we are. Now, if we just, again, multiply p by x, okay? If we just multiply p by x, and now if we have p as written in this form, okay? And x is written in this form, therefore, P will be first multiplied with this guy. Also, P will be multiplied with C. P multiplied with C will be 0. Therefore, your projection on the image plane will be nothing but your lambda P times the homogeneous representation of the arbitrary point A. Okay, this is an arbitrary point A. Now, the question is, why am I telling this? I would like to find a technique from image points. How do you obtain some rays going to infinity? Therefore, I'm talking this thing. Okay, this is your image plane. There is a small x. This is the C camera. I would like to obtain a ray going to infinity. I know the projection P matrix. Okay, and I would like to write something going backwards. Now, we know that the pseudo inverse of P, okay, which is P transpose inverse. First things first, this is the pseudo inverse. If I multiply this thing by P, okay, if I just simply multiply this thing by P, okay, certainly the result will be an identity operator. Therefore, what I'm saying is this. P pseudo inverse is a point in 3D space. Okay, that's a point, homogeneous 4 by 1. There is another point, the C. Okay, if I simply write them in this form, one point, another point, weighted sum, that will be something going to infinity. Okay, therefore, now I realize this. If I call this x lambda, I hope everybody is seeing this fact. If you multiply left and right, this 3D point, P times P plus x is lambda P times C. That is equal to 0. That is equal to identity. And this is nothing but x point projected by P, giving us the result x. Okay? Therefore, this is what we are after. This is how we back project image points to rays going to infinity. Okay? Simply the pseudo inverse of your projection matrix, and you have to add the point C camera origin, and the lambda parameter is just showing where your infinite ray is, the parametric variable of your ray. Okay, now one little thing to note, this projection matrix that we are talking about consists of P1 transpose, P2 transpose, and P3 transpose, okay? And it is multiplied with your X homogeneous. And it is giving you at the end X, Y, and 1, okay? This is your nothing but your projection operation. Now, what we are saying is if you just take the last row, if you multiply with this, you have to obtain this result. But please note, our results are always up to a scale. This is homogeneous. There is an unknown W. Okay, there is an unknown W, and that is in general for arbitrary W's that X point is correct. But what I'm realizing is this. If you look at P3 times X, your P3 transpose times your X should give me nothing but W. Okay, and that W in fact is nothing but your depth of your point. Okay, in other words, that's the value X and Y. Okay, we have seen that X, Y, and 1 is an point representation in P2. Okay, and what we are having is as soon as you have this W, in fact this W also controls this point on this ray, and depending on the value of this W, you are talking about the depth of the point X. Okay, now after this little introduction, let's look at this fundamental concepts of the epipolar geometry, although we have seen a little bit about these things, but let's look at more. Now, this is our arbitrary geometry point, image plane P and P prime. Okay, this is your P point P up the axis. Okay, the centers. Now this is the epipolar line. This is the epipolar plane. Let's define them. Okay, let's define them one by one. The yellow one is the epipolar plane. These are the epipoles between the centers, the epipolar lines. The baseline between two cameras, the red one, okay? And we are, if you just define it once more, we did it before, but baseline, line joining the camera centers, epipoles is the intersection of the baseline with image planes, epipolar plane is the plane containing baseline and the world point, and the epipolar line is the intersection of the epipolar plane with the image plane. All the epipolar lines intersect at the epipole, we have seen this, and epipolar lines intersect the left-right planes in the epipolar lines. Okay, now let's try to come up with a relation about this geometric concept into an algebraic relation. Okay, now as you can see, as soon as you fix the point P here, there could be many options. Okay, this is fixed for us, and this P point you just draw a back projection, and maybe your point is here, here, or here, but you don't know where it is. Okay, therefore the potential matches, assuming this is one projection of this point P, the corresponding projections could be on P1 prime, P2 prime, P prime, or epipolar plane. Okay, any one of them, it could be the case. Now, right now, we are trying to find a match for us, and we realize that the only thing we can have is a point on one image and a line on the other image, okay? And this is called the epipolar line. Now, as you can see, for example, a P point over there similarly creates a red line on the other image, the corresponding epipolar line for that P prime point. What we are talking about is this. If you have two images, left and right, they are not exactly equal. If you look at carefully, you will see the differences. Okay, for example, this is not available here, slightly different. Therefore, this point, if you draw the epipolar line, it is this. It is passing through the correct point. If you have this point, this is the epipolar line, it is crossing here. If you just draw the epipolar line of this one, that's also available here, okay? Therefore, it's cutting through the correct correspondence, but we don't know exactly where it is right now. And finally, this is the same here. It should be this point. Similarly, this example. Now, the question is, okay, this is beautiful, but I would like to obtain a mathematical relation between them. Let's try to obtain, assuming the camera is calibrated. We know how the rotation and translation values are. Okay, from one frame to the other frame, we know how to transform these things. Okay, now rotation is 3 by 3, translation is 3 by 1. Now let's assume you have this P point. Okay, now this is XY. In the previous things I was writing 1 here, but if you write an F over there, this will be nothing but the focal length distance. Okay, therefore this point XYF is nothing but your distance, okay, which is exactly the epipolar, the image plane distance in this direction, okay? In this direction you have F, and that F is giving you X, Y, and F, and therefore this point is giving us a point on here, okay? Now, similarly, you can write this P prime as well. Now, let's assume a camera-centered coordinate system with such a relation, okay? Now, let's remember a few things. The cross product, if you have a cross product, C is orthogonal both A and B. Therefore, A dot C and B dot C are both equal to 0. We will just use this fact in the next slide. Now, let's have this relation here. Let's have this relation here. This is your X, this point is written with respect to this coordinate system. This is X prime. And it is written with respect to this coordinate system. The green one is the X, okay? Now, in two different coordinate systems, we are writing this. T is written in this coordinate system, okay? Therefore, I can have this one and that one in the same coordinate system. Now, multiplying with R, hopefully, make this X also in the prime coordinate system as well. Now, one little trick before moving, I multiply both sides with T vector as a cross product. Okay, T vector as a cross product, I multiply here, obviously the other side as well. And this is obviously normal to the plane. Which plane? We are talking about the yellow and the red makes a plane for us. And that is just from maybe from outside the display of your screens. We have a normal, that dot product. If you continue multiplication of the T on two terms here, the first one will be here, T cross Rx. Okay, let's leave it as is. But the other one, a vector multiply cross product by itself is equal to 0. Okay, and you obtain nothing but this thing. Now we have a vector which is normal to this plane, which is equal to written in this way. Now, I learned one thing at this point. This is giving us something outside the display, and which is in terms of T and R, two transforms of the transformation posed between two cameras. Now, if you simply multiply, the yellow vector with the vector which is normal to the plane, obviously this dot product, that dot product should be exactly equal to 0. Okay, therefore that dot product is exactly equal to 0. Please note that if you take the dot product here left hand side, the right hand side will also be dot product here. Therefore this dot product should be equal to 0. Remember we did before matrix form of the cross product. Our this skew symmetric matrix, diagonals are equal to 0. Therefore, A cross B, you write the entries of AX, BY, AX, AY, AZ like this form as a matrix 3 by 3, and B is stored like that. The cross product, the values are obtained in this way. And obviously, as we talked before, if you take the dot product of A with this resulting normal vector, they should be equal to 0. Okay, therefore we did these things. I just obtained, and therefore whenever we have a cross product, I prefer to write it as a matrix 3 by 3 times the vector. Okay, now we were stopped at this point. That is the equation that we have. I'm going to use this equation. Maybe you are not realizing Rx is a vector, T is a vector, cross product Rx is also a vector. Therefore, I just multiply the inner product. And now the T cross Rx, I'm going to do a little trick here. I'm just write this thing as a matrix form, a matrix, another matrix, and you multiply like this. Now just look at carefully here. I'm talking about this. There is a vector, there is a matrix, there is another matrix, inner product with this guy. Okay, it's like this. Therefore, I can say that this is your T cross, this is your R. Now, if you look at carefully, if you put into this parentheses here, I'm talking about nothing but my 2 matrix multiplication, and the whole thing, by the way, it's equal to 0. Okay, and we obtain this result. Now, let's call this multiplication of these two 3 by 3 matrices as E for essential. Okay, now let's see what do we move from here. Therefore, from the left I multiply with the vector x prime. From the right I'll multiply with the x, and E matrix is in the middle, and this multiplication is a scalar at the end. 1 by 3, 3 by 3, 3 by 1 is 1 by 1. It's equal to 0. Okay, now this is saying that this result is for arbitrary points. Okay, this result is true for this written in these two terms. But please note the rays from P and P prime, these guys which are going to the infinity, they also satisfy. Not the x point over there as a 3-dimensional point. Here I can say that the small x and the small x prime written in the homogeneous coordinates also satisfies this thing. That's the important part. Please note, at this point I was in Euclidean space. There was nothing homogeneous. Everything was in R3. Now I am talking about these points, but these points are in the homogeneous coordinates. What I'm saying is this point here, if you just multiply with a homogeneous term, it will continue like this. Therefore, the vector x, y, f, okay, that homogeneous term also satisfies this relation, okay? And this E is called essential matrix by Longut and Higgins in 1981. And I write this in terms of image points, and those image points, but obviously I use focal length. This is a calibrated system right now. I know X, Y as metric information. This video, this part is about completely calibrated stuff. Therefore, that P matrix is equal to, that T matrix is equal to something like this, okay, X, Y, and F. Okay, therefore, it is like this. Therefore, this distance is F. Therefore, you have a point here. That point is X, Y, and F. And this is metric information. F is also metric. And everything is right now in camera coordinates, okay? Now, the thing is, this matrix is nothing but defining also mathematically, algebraically, the line information. Let's remember one fundamental fact here. Let me open this. Let me write it here. there was this relation, and line transpose L is X on the image plane, X transpose L is 0. Okay, I was writing these equations on the image plane. Maybe you remember in the previous chapters. That is an X point, like homogeneous X, Y, and 1. Okay, and there is a line here, A, B, and C. And ax plus by plus c is equal to 0 is the line equation. That was the thing I was talking about previously. Now, would you please look at here? There is a p. This is your p here, and your p transpose p prime transpose e is your L. Therefore, I'm talking about p prime transpose is e is equal to like ABC. Okay, this is your ABC, and we are having this is the line equation, and that line equation is giving us the epipolar line on this plane. Okay, therefore the point is here that L prime satisfying this point is obtained from the P prime point. The P prime point is here, please note, this is the P prime point. Okay, that P prime point is basically multiplied with E, and that E is creating the epipolar line. This is very logical. I was saying that the line, a point on the other plane defines the epipolar line on the other image plane. This is exactly what we are doing right now. I define a P prime by the help of E matrix, which is consisting of rotation and translation. I just map this to a line, and that line is epipolar line. Okay, therefore E transpose P prime or P transpose E, because please note that should be equal to your I just write it long, this is L transpose. Okay, this is L transpose, therefore the transpose of this thing is equal to your line equation. Okay, now what are the properties of our essential matrix? First of all, it is a result of rotation and translation between two camera systems. Nothing but pure transformation, rotation and translation. They are multiplied as matrices. There is a single matrix E, essential 3 by 3, which is giving us a summary of the pose between camera 1 and camera 2. Right now, I assume K is known, intrinsic parameters are known. I am using focal length F, all these things. Okay. Now, if we look at more, we will see this is our essential matrix. Although I haven't solved, but later I'm gonna show how to solve this. There are 4 solutions for rotation and translation. Here are your solutions. Point, 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 point. These are 3D points shown in from the top. A, B are 2 cameras. This is the image plane, this is the image plane, this is the focal length, this is the focal length. Please note, this camera and that camera, they are far away with the same amount with each other. Their orientations are more or less the same, and more importantly, the dots, the red dots on A image and the yellow dots on the B image are exactly equal. These points will be our measurements that we feed to our system to find rotation and translation. This, and this, they are giving exactly the same 2D correspondences to your algorithm. The algorithm should be selecting either this one, that one, or that one. Please note, but all of them basically satisfy pinhole camera. What they don't satisfy is, in our case, our points are in front of the camera. Only this A part, this guy, all the points are in front of the camera. If you look at here, both of them are behind the camera. If you look at here, one of them is in front, one of them is behind. If you look at here, one of them is behind, one of them is in front, but only this one, you will have the correct solution. Therefore, you have to wait so that you also extract the 3D information. If they are positive in front of you, that it will be your solution. Okay, and one little thing I'm giving without a proof, but there's a beautiful proof in the book by Hartley and Zisserman. This E matrix, this is not arbitrary 9 numbers, okay? The E matrix here is not arbitrary. Okay, what I'm saying is this. This is not arbitrary. This is a matrix, okay? This is a matrix where U and V transpose, and very interestingly, your eigenvalues 1, 1, and 0, okay? Your eigenvalues are 1, 1, and 0. That's a very important thing. The proof is in the book. You can look at it. The reason of, first of all, why this is the case, why should be such a thing happens. Please note, this matrix is a little bit not arbitrary. It's skew symmetric. This is also not arbitrary. This is rotation. There is a theorem in math, a skew symmetric matrix multiplied with a rotation matrix orthonormal. Their multiplication should yield such a thing. Now, why am I telling this? This 110 will later help us. Another thing is, for example, you try to estimate E matrix from point correspondences. If you write your constraint equations, assuming you have 9 arbitrary numbers, in fact, 8 of them are it's homogeneous, therefore 8 of them is independent, 1 of them is arbitrary. If you assume that you have 8 arbitrary numbers, wrong. You have to put these constraints. You have to do something so that such a constraint is also inserted to your problem so that your estimated E matrix is a real essential matrix. Multiplication of a skew symmetric and an orthonormal matrix together. I think, yeah, that's all for this video. I'm gonna stop here. That's our third one. The fourth one will follow, where I will not assume any calibration. From the real pixel locations, I will try to solve for another matrix. Next video.